We're going to talk a little bit about commercial orbital logistics because you need to solve that problem in order to utilize propellant in space, and that's what our asteroid mining ambitions are all about first. We're also going to talk a little bit about our lunar polar power. I was disappointed to see that NASA wasn't looking at towers. Modest tower can really help duty cycle in a lot of those locations. Optical mining of asteroids. A lot of the work there has been done here in the laboratory with Chris Dreyer and Timothy, who is on his PhD committee, so that's very exciting. And then telescopes to prospect for our ISRU. So those are the things we're going to be talking about. But let me first tell you a little bit about where we are at TransAstra. TransAstra, we're so glad that we have won 7 NIAC awards in the last 5 years, including we're one of the first 2 companies to win the first NIAC Phase 3. That's allowed us to scale the company and bring in about $7 million of private sector venture from Silicon Valley. Very cool. That's our new facility. It's a 7,000 square foot facility called the Hive, because most of our flight systems are named on things that have to do with bees, because we realize that asteroid mining is more like harvesting than mining. The mining analogy really breaks down. We've got 2 vacuum systems like this one here, each a couple of cubic meters. And if you look at this pumping plant, that's a 6,000 CFM pumping plant. So we can run 2 multi-kilowatt solar thermal rockets simultaneously. We have 64 kilowatts of solar simulator in our lab, a network of top university professors, including Professor Dreyer here, many others, skills and facilities for ISRU, propulsion, optics, microwave engineering, thermal engineering, space system design, and we have a really world-class trajectory analysis capability that you actually need to do solar thermal propulsion right. So I'm going to talk a little bit about our lunar ISRU work. That was funded in 2 NIAC activities, a Phase 1 and a Phase 2. And the focus of that is the Lunar Propellant Mining Outpost, which we're doing collaboratively with Blue Origin. I don't see Blue Origin here today, but it was really cool to see Honeybee. The quality of the engineering at Honeybee just blows my mind. Managing a team of engineers, I really appreciate what Chris Acne and the team there have done. We invented this concept called Sunflower, which uses tensegrity towers to get solar reflectors up into the sunlight. Originally, we looked at doing that with tensegrity. Another type of tensegrity tower is an inflatable tower. It turns out when you do the physics on inflatable towers, they can go kilometers high on the moon with reasonable payload fractions. And we prototyped that, and we've patented it. Why power towers on the moon? Because ISRU is a very power-intensive process. No gallons of water without lots of megajoules of energy. So that's critical to making ISRU happen. This is a picture of our tensegrity tower prototype that we demonstrated under our Phase 2 LPMO NIAC funding in collaboration with Blue Origin. That was really cool. And what we concluded from that is we don't really want to work with tensegrity structures. So because they work really well on paper, very difficult to practically engineer in person. But another type of tensegrity structure that people don't realize is tensegrity is thin film inflatables. When you account for all the leakage, because these are actually a vacuum inside the inflatable in the lunar environment, not much gas in there. When you account for all the inflatables and everything, inflatable towers can hold tremendous masses on the moon. You could hold a city on the moon, kilometers above the surface, if you wanted to. So we've demonstrated that. We're very excited about that. It's patented, and we're moving forward in that area. Also, these towers don't have to be gigantic, grandiose things. 10 meters, 15 meters, 20 meters really does improve the duty cycle in a lot of places near the edges of significant PSRs. And I really appreciate the work. I see Dan Britt here. Thank you for the leadership that you've provided in that area and your postdocs. And we've recently extended our modeling capability there with University of Central Florida. Very exciting. We also have a patent pending, I think, in the area of lunar ISRU. We have a really great microwave engineering team at TransAstra, a significant multi-meter Faraday cage that we can put many kilowatts of microwave power in for experiments on microwave heating of lunar regolith for driving volatiles out, and also for sintering bricks for making landing pads and that sort of thing. We've kind of put that work on hold recently because we've been working like heck to scale the company, as we've scaled from 5 engineers a year ago to in excess of 30 today, from working out of my garage to a 7,000 square foot facility and raising $7 million of venture funding. We've been a little busy. So where's Ron Turner? So Ron, thank you for letting us extend those contracts so we could do that scaling. It's going to be really exciting when we shift back into that and show you guys those results. Asteroid mining, I think every year that I presented at the SRR, I've shown this chart, this picture. That's a carbonaceous asteroid, a meteorite, in a test tube heated over a Bunsen burner. It's not that hard to get water out of carbonaceous asteroids. It's just heat. So what's the simplest way to do that and the most practical way to do that for ISRU? We invented a process that's patented, many more pending, called optical mining, where we use simple, lightweight solar concentrators to concentrate sunlight onto the surface of the asteroid. And we've demonstrated in the laboratory dozens of times here at Colorado School of Mines, and now we've got about 4 times that capability in our lab in Southern California. We're going to be extending that work, showing that you don't have to touch an asteroid to mine it. Capture it in a bag. By the way, if you don't capture the asteroid in the bag, forget it. That's ridiculous. You see these startup companies repeating exactly what DSI and PRI have done. It's really funny that they haven't learned from the lessons of past. Capture asteroids in bags, use sunlight to mine them. That's the way to go. Here's the facility here at CSM. Pretty great facility. We love working with the folks here. There's a photograph of one of the mining experiments. There are dozens of videos online where you can see that happening. It's very exciting. We love it. This is the Mini Bee flight prototype system. We have hardware in our lab at TransAstra where we're testing these components. This hardware was developed under our NIAC Phase 3 funding, which we deeply appreciate. When we originally made that proposal, it had $1 million in matching funds. We're putting about $4 million of actual matching funds into that effort. The Mini Bee concept, it's a spacecraft about this big. Each of those reflectors is 1 meter in diameter for scale. It fits into an Espa Grande. We launched the spacecraft and a simulated asteroid into space on a Falcon 9. One of the things that it uses is solar thermal propulsion. Why do people drive internal combustion engines in the year 2022? Why do they drive cars like that? Because they haven't realized that their vehicles are obsolete. Why do people still fly chemical rocket engines and 20th century style electric propulsion in the year 2022? Right now we have a Dragon sitting on a pad surrounded by a toxic cloud. They're trying to figure out where the leak came from and those toxic chemicals. Chemical propulsion systems in low Earth orbit are generally carcinogenic, always explosive, and poisonous. How many people know that the astronauts on the Apollo Soyuz test mission actually all came down with lung embolisms because they opened the bleed valve on the command and service module too early and got hypergolic propellants in their lungs? Chemical propulsion systems are dangerous and toxic and expensive. Electric propulsion systems, I did my PhD in electric propulsion. It was a great technology for the 20th century. Also makes a lot of sense for station keeping and orbital deployment on communication satellites where there's lots of power. But it costs $10 to $20 million a newton just for the thrust. And that's not affordable in the 21st century. And they're slug slow. A fast electric propulsion system can go from 0 to 60 in 3 days. That's why it takes a year to get to the moon. More than half a century went to the moon in 4-5 days. A year to get to the moon is ridiculous. We need better technology, and that's why we're working on the solar thermal rocket. Right now, our solar thermal rockets in test generate newtons of thrust running on water, propellant that you can drink. Later, we'll upgrade to liquid hydrogen, and they'll provide nuclear rocket-like performance at about 1% of the cost of a nuclear rocket. So we really appreciate the NIAC program giving us the funding to demonstrate these technologies that we're very excited about. This is just the optical systems. We have a significant optical systems lab at our company. This is the laser alignment system for our patented optical alignment system that allows low-cost solar reflectors to track on the sun with spacecraft that don't have exquisite attitude control systems. Worker Bee Orbit Transfer Vehicle version 1 is the mini Bee that you saw earlier without the optical mining demonstrator. It launches in an Grande size payload on a Falcon 9. With that, it can carry payloads of up to a couple hundred kilograms and has a maximum delta V capability of a couple of kilometers per second. We can deploy 96 small sats by flying 24 Worker B1s on a single Falcon 9 and spread them through a range of inclinations of 30 degrees. In other words, we can deploy an entire global constellation in a couple of weeks. It's the only system like it in the world. And that's why our investors are so excited about it. The next thing I want to talk to you about is our telescope technology. Several years ago, when we started the company, we realized the real problem with asteroid mining is finding dark moving objects in space. We know that there are 1 billion near-Earth asteroids of size greater than a few meters spread throughout the inner solar system. The number of small asteroids with very low delta Vs relative to the Earth, we know from statistical models, represent numbers in the thousands and represents $1 trillion resource of minerals and hundreds of billions of dollars worth of propellant. The problem is, for those small dark asteroids, we only know where about 10 of them are. We know where all the big ones are, but we only know where 0.003% of the small dark asteroids are. So we started working on a breakthrough technology to find the small dark asteroids. We call that Suter telescope technology because it's named after Sutter's Mill, where in California they discovered gold, and it led to the gold rush of the American West. We think the Suter telescope will lead to the gold rush to space. There are a number of innovations involved in Suter, but the important thing that I want you to remember is that we now have Suter telescopes operating in an observatory in Tucson, and we're proving the algorithm and finding fate-moving targets every night. Here's another thing that's really cool about it that's related to everyone's interest in the development of space. The same technology that finds faint, dark, moving asteroids can find orbital debris in space traffic, something that's of acute interest to the Space Force. So we're moving into commercial operations for that to help to pay for our vision for space industrialization. Originally, when we started working in this, we had a hard time publishing in the refereed literature and winning proposals because people said it was just too good to be true. Ron might remember there was a reviewer at one point who said, you made a 4-order of magnitude error in your estimate of the faint moving objects you could find. We double and triple checked that calculation. We went back in our refereed publications with reviewers and proved that this technology is 300,000 times more effective in finding dark moving objects in space than conventional telescopes. With a telescope that's this big and that big around, we can find dark moving objects in space that can't be found with the $1 billion Pan-STARRS telescope. That's super exciting. And this is just how you add up all the factors to get to that 300,000 times more effective asteroid finding. So the idea is finding faint moving objects in space is critical if we're going to be spacefaring, because we have to get through low Earth orbit, and if we don't find the debris and the traffic hazards, that's a problem. We have a member of our board who's an astronaut, Dr. Stan Love, who was my best ever student when I used to teach at Caltech. And he confirmed to us that the single greatest hazard to astronauts on space missions in low Earth orbit today is orbital debris. It's a real problem, and it's getting worse. That's why the Space Force is taking it so seriously. It's incredibly cool that the same technology that we can use for asteroid prospecting also finds those targets in space. The issue is that these targets move too fast through the pixels of large telescopes. Our plan is to take Suter and move it into space with a mission we call Suter Ultra. But the core of Suter is something called match filter tracking. optimized match filter tracking is patent pending. Here's the problem with finding dark moving objects in space. If you take a short exposure in space, you get the bright stars. If you take a long exposure, the faint objects start to show up. But any moving object doesn't get brighter. So anything that's below the signal to noise ratio detection threshold does not appear. So what do we do about it? We postulate or guess the tracks of possible moving objects in space. And we take exposures using CMOS detectors, the same kind that are in your iPhone, your Android, and we see if they add up along different trajectories. That requires a lot of computational power that can be done on either a GPU or space-qualified FPGA like the Vertex 7. It's within the capability of the Vertex 7. We're doing this right now every night at our observatory. We also have invented a way to use a lot of little telescopes in a way that's much more powerful than a single telescope. For the Suter Ultra mission, we would have 109 telescopes, but not all packed together. They form a cross in space looking away from the sun. And then we take that cross and we just rotate the whole spacecraft, no moving parts. By the way, we're doing this in our compound telescope on the ground every night today. And we move this cross at the same speed as the targets that are going through. And what that allows us to do is to see a region of space with a relatively small number of telescopes that would take many times more telescopes to do. So a lot of these, so the match filter tracking gives you a factor of about 100, and then these other factors all add up, eventually get to 300,000. I'm very excited. We do rapid, agile development at TransAstra. We're in our third rev of the telescopes at the Weiner Observatory in Tucson. Our plan is to fly them on our worker Bee OTV in low Earth orbit to demonstrate Suter technology. We think the Space Force will pay for that because it'll help them with traffic monitoring, but it takes us to the operational missions. Now, we can fit 3 Suter Ultra spacecraft on a single Falcon 9. Each one carries 109 12-inch telescopes that can be done commercially. So we're putting more than 300 telescopes in space with one Falcon 9 launch. Initially, we will fly them into cislunar space. In this particular case, this shows a Suter Ultra at L4 and L5 and also at L2. With that, we can monitor all the traffic in cislunar space down to CubeSat size. That's a total revolution in space domain awareness. And there's a commercial market for that, there's a defense market for that, and there's a science market for those capabilities right now, today. But the ultimate is to put it in heliocentric space. We've innovated a new type of heliocentric orbit, a slightly elliptical orbit around the sun that causes the spacecraft to rotate or go around the Earth in a retrograde orbit outside the Earth-Moon Hillsphere. What's beautiful about that is that the telescopes are always right at the distance that you want to be to find Earth-approaching asteroids in an optimal way for either asteroid mining or planetary defense. So this can be the last line of defense against all those asteroids that we don't know about. We know where all the big ones are. We know where almost none of the little ones are. Like I said, 0.003%. So the legacy of this concept is the Sutter's Mill from Northern California, where in the 1900s they discovered gold. That led to the settlement of the West. And we think that this resource, that this capability, will lead to the gold rush to space. And by the way, this is our Queen Bee asteroid mining vehicle, which is conceived as being the asteroid mining version of our worker Bee 3, which is a system that takes the full capability of a Blue Origin New Glenn. The vision here is millions of people living and working in space for the betterment of humanity and harvesting of resources out of the biosphere so that humanity can have an infinite, exciting future. So this is our roadmap. I just outlined it all to you. There'll be a quiz on this later. Worker B1, small. Worker B2, medium. Worker B3, heavy lift. as we move from current small-sat orbital operations to more capable systems in low Earth orbit, to cislunar space and beyond. So this is kind of a hokey picture, kind of an old-fashioned picture of a couple of folks standing there. People rib me about it. But the reason I like this picture is because it tells a story. People are going into space, and they're going to raise families, and they're going to fall in love. Our vision is to tap into those resources so that our children and their children and their children can have better lives without straining the biosphere of the Earth.